Thank you very much for participating. We develop and provide J-OCTA, a molecular simulation software for materials design. In this presentation, we will give an overview, how molecular simulation can be used to obtain material properties. If you don't have any experience in this area, we will explain it to you, so that you can understand it. If you have any questions, please feel free to let us know after this presentation. At first, let us introduce our company. Our company, J-Soul Corporation, is in Japan, and the head office is in Tokyo. We have 1,200 employees. And one division is focusing on simulation field. Our company's business is system integration and computer simulation. We are treating more than 20 simulation software, including macroscopic and microscopic field. Software that starts with the name, J, is what we develop, and sell worldwide. So, J-OCTA is developed by J-Soul. Siesta, DFT engine is supported by Shimune, in Spain. We would like to appeal, we have enough experience in many field, for example R&D, production engineering, and product design. Here is the historical background of our software. J-OCTA is our software, but it's based on the free version of Octa, which was developed as a Japanese national project around 2000. Many manufacturing companies participated in it. Several simulation engines, a simple modeling GUI and a Python scripting interface were developed. It is still being upgraded and distributed by i-Rheo, a Japanese research institute. We can count the number of users on our BBS and it is over 3,000. Springer has published a book about it. Please refer to it if you are interested. One of our recent topics is the integration with Materials Informatics. Octa has been adopted as the platform for a national project on Materials Informatics in Japan. This has resulted in additional capabilities related to machine learning and deep learning. J-OCTA is being developed by J-Soul as a commercial version of Octa. Basically, J-OCTA includes modeling tools for using each engine in Octa. One parallelized engine is also included. The user base is mainly industry, and more than 100 companies have installed this software. The latest version of Octa, which is freeware, is still under development, and the latest version is 8.3, but 8.4 will be released soon. The latest version of J-OCTA is compatible with 8.3, but we will support it as soon as there is an upgrade of Octa. In addition, an enhanced Octa is also being developed to handle images, support large-scale systems, and add machine learning capabilities. You can download it from Octa BBS. The graph below shows the number of registered users of Octa BBS and it has been expanding to more than 3,000 users in 2020. This slide shows the percentage of users of J-OCTA. Roughly speaking, the ratio is 40% for chemical and material manufacturers, 20% for automotive and tire, 20% for electronics, and 20% for research institutions. We have maintained these ratios recently, but 15 years ago the ratio of chemical and material were 80%. Recently, molecular simulations have been widely used in the materials department of machinery manufacturers. If you are interested in this, please visit our website. You can find information on lectures and technical information from past user meetings. What kind of material design is needed? As an example, this slide summarizes the materials needed in the automotive industry in recent years. First, materials needed for electrification include electrodes, electrolytes, separators, and binders for lithium and fuel cells. Other materials include magnets for motors, semiconductor devices, and their encapsulation materials. Material properties such as heat resistance, thermal conductivity, thermal expansion, stiffness, and adhesiveness are important. Next, the physical properties of fiber-reinforced plastics and thermoplastic elastomers used to reduce weight. Fiber-reinforced plastics are used as an alternative to metal materials. Thermoplastic elastomers are lightweight because they do not contain fillers. Mechanical and fracture properties, such as stiffness, are design factors in these materials. Next, let's look at low rolling resistance tires. This covers rubber composites, and these include carbon black and silica. Physical properties, such as viscoelasticity, are important for rolling resistance, which affects grip performance and fuel efficiency. Finally, I would like to talk about electronic materials, which are important for 5G communication and other applications. Low dielectric constant, thermal resistance, and moisture resistance are important here. As you can see, the optimization of basic material properties is important in all cases. In this seminar, we will introduce an example of how these fundamental properties were evaluated by molecular simulation. J-OCTA has some simulation engines from nanometer to micrometer scale. They have unique names. Siesta is the density functional theory engine based on quantum mechanics. Electron state, interaction, polarization, and reaction are evaluated. In this field, ABU-init MP is used to estimate interaction parameter based on the fragment molecular orbital method. And J-OCTA has interface with Firefly, Gaussian, and MOPAC as external engines. About the molecular dynamics, Cognac and VSOP are default engines in J-OCTA. Molecular structure and many properties like thermomechanics and diffusion can be evaluated. And external engines such as lamps, Gromix and HUMD can be used as well. Pasta and Naples are based on the tube model of polymer entanglement system. Viscoelastic properties can be calculated especially about polymer melt and solutions. Sushi is the mean field engine to calculate the phase-separated structure. Polymer blend including block copolymers are simulation targets. Muffin is based on the continuum mechanics especially for the elastic finite element analysis for phase-separated structures obtained by sushi. And we have direct interface with LS-DYNA to conduct nonlinear structural analysis as an external engine. Capsule is for colloidal dispersion system based on the fluid dynamics. As you can see, several arrows connect each engine. Multiscale simulations are possible by using parameters obtained from the lower scale in the upper scale, or by using the structure obtained from the upper scale as the initial structure of the lower scale. J-OCTA includes several functions for this purpose. This slide is about J-OCTA's modeling tools. You can create a molecular structure by drawing a chemical formula as shown in the upper left figure. Molecular mechanics calculations are performed by assigning force field parameters, and then quantum chemical calculations are performed. The force field parameters will be introduced in the next slide. Next, look at the lower left figure. It is also possible to read molecular and crystal structures described in mole and CIF files. The force field parameters can be set from these structures. The upper right figure shows the crystal structure of silica and the interface structure of polymer. Modeling of such complex systems, including surface modification, can be easily realized by novice users. The figure on the right shows one of the strengths of J-OCTA, which, when combined with the MD engine VSOP, facilitates the setup and execution of chemical reaction calculations using molecular dynamics. In particular, it can be used to calculate the curing reaction of thermosetting resins and subsequently evaluate the material properties. Specific examples will be introduced later. This slide is about the force field parameters used in full atomistic molecular dynamics. The force field parameter sets shown in the upper left list are registered in the J-OCTA DB. Direct force field is a commercial parameter set, and J-OCTA has an interface to it. The lower left figure shows the correction function of the force field parameters. The potential parameters for the bond length, angle, and dihedral angle potentials are adjusted based on the results of quantum chemical calculations. The lower left figure shows the function for estimating the LJ potential parameters at the interface between inorganic and organic materials. This can be used to evaluate the van der Waals force by performing DFT calculations using siesta. The obtained results are used to determine the parameters to be used in the MD calculation. As a result, it is possible to calculate complex molecules and interfaces as shown in the upper right. In the calculation of the interface structure, the EAM potential is used inside the metal, which can be applied to calculations such as heat conduction. J-OCTA has Siesta Modeler, to set up and run Siesta on the GUI. DFT is an abbreviation for Density Functional Theory. The Siesta Modeler is a different version of ASAP Pro, developed by Shimune, a Spanish company. With the Siesta Modeler, you can perform single-point DFT calculations, structural optimization, band structure, nudged elastic band, equation of state, vibration, and phonon analyses. In future versions, the ability to perform first principles molecular dynamics will be added. DFT can be used to analyze the electronic state and spin of materials. The NEB function can also be used to analyze the activation energy in chemical reactions. The EOS function can be used to calculate the bulk modulus of a solid, and phonon analysis can provide information on the lattice-specific heat. First principles molecular dynamics can also be used to analyze thermal expansion and reactions. Coarse-grained models are needed to perform molecular dynamics on a larger scale. In coarse-grained models, several atoms are used as a single unit, and the potentials between units are defined. It is possible to estimate the coarse-grained potential, based on the structure and potential of the all-atom model. As shown in the upper right figure, coarse-grained units are set in the GUI. By analyzing the results of all-atom molecular dynamics calculations, the distribution of distances and angles between atomic clusters are evaluated. Finally, potentials are then determined based on Boltzmann's formula. For the non-bond potential, the potential between coarse-grained units can be determined by using the iterative Boltzmann inversion method, or a Monte Carlo-based method. After coarse-grained molecular dynamics has been performed, it can then be mapped to an all-atom model. We call this reverse mapping or back mapping. To predict the phase-separated structure, either the mean field method or dissipative particle dynamics can be used. The modeling procedure is the same as for coarse-grained molecular dynamics. Draw the chemical equation on J-OCTA and set the coarse-grained unit. The upper figure shows an example of a phase separation structure formed by polyelectrolyte and water, calculated using DPD. Red is hydrophobic groups, green is hydrophilic groups, and blue is water. This material is used in the electrolyte membranes of fuel cells. To perform such a calculation, the interaction parameters between the coarse-grained units need to be determined. In this field, this parameter is called the Flory-Huggins chi parameter. To obtain the chi parameter, three methods are provided. The first is to use phase diagrams obtained from experiments, which are not described here. The second is to calculate the contact energy and number of contacts between coarse-grained units based on an all-atom model using a Monte Carlo method. For the energy calculation, it is possible to use a force field or quantum chemical calculations. For quantum chemical calculations, a tool called FSUS is used, in which the fragment MO engine called ABINIT-MP is used. Third, the chi parameter is calculated based on the difference in solubility parameters between the two components. The solubility parameters can be estimated using the group contribution method or molecular dynamics, the latter of which can take into account the contribution of the volume fractions of the components. J-OCTA includes several methods to realize multiscale analysis. In the upper left figure, the phase-separated structure obtained by the mean field method and DPD is used as the initial structure for coarse grained MD. The molecular configuration is determined by a Monte Carlo method using a density field. The phase-separated structure shown in the figure cannot be obtained by molecular dynamics, due to insufficient computational time. The mean field method, on the other hand, can be used to calculate the equilibrium state. The results are then used in MD. In the upper right figure, the phase-separated structure, obtained by the mean field method is also used, in a continuum-level finite element method calculation. The density distribution is replaced by the elastic modulus distribution. This allows us to deal with the deformation of the phase-separated structure of materials, with different elastic moduli. It makes it possible to calculate the average elastic modulus, stress concentration during deformation, and so on. In the figure below, the initial structure of all atom model is obtained based on the results of coarse-grained MD. The time domain that can be calculated for all atom MD is limited. On the other hand, it is possible to obtain the structure of a molecular chain that has been sufficiently relaxed by coarse-grained MD. By reverse mapping from coarse-grained model to all atom model, we can obtain the amorphous structure required for all atom MD. J-OCTA includes modeling tools for the finite element method at the microscale. J-OCTA originally contains a finite element method engine called Muffin, but it also has interfaces with LS-DYNA and DIGIMAT as external engines. The upper figure shows the phase-separated structure obtained by the mean field method, converted to a voxel mesh. LS-DYNA input is created and nonlinear structural analysis is performed. In the lower figure, the fiber dispersion structure was created on J-OCTA, loaded into DIGIMAT, and the mesh was created. In general software, it is sometimes difficult to create highly packed structures of fibers and particles, but this can be achieved by using J-OCTA's Cognac. In this slide, we introduce the machine learning function of J-OCTA. J-OCTA's modeling functions can be called from Python script. This means, without modeling on the GUI, J-OCTA can automatically create the corresponding 3D structure, and even bulk structure, by providing many smiles format data. Molecular simulations are then automatically executed, and the obtained properties are stored in a database. In addition, the system can perform deep learning of the relationship between physical properties and molecular structure. This makes it possible to estimate the properties of unknown materials. This technology is commonly referred to as QSPR. Recently, a technology to calculate the structure of a material in order to obtain a target property is also available, and J-OCTA plans to provide such a function. This slide is about the latest topics. i-Rheo GT is the new method for converting relaxation modulus GT into complex dynamic modulus G' and G double prime. GT is obtained by the molecular simulation. This method is optimized Fourier transform for time series data. You can use i-Rheo GT on J-OCTA GUI. In addition, J-OCTA has a curve fitting function with generalized Maxwell model. With this function, we can fit generalized Maxwell model, Prony series, to the data of relaxation modulus GT, which is obtained by simulation engines. The data are fitted by nonlinear least squares. According to the coefficients of Prony series, complex dynamic moduli are evaluated simultaneously. From here, we would like to introduce some examples of material properties evaluated using J-OCTA. We will gradually move from a small scale to a large scale. Here, density functional theory is used to evaluate the adsorption energy of organic molecules on inorganic crystals. In order to correctly evaluate intermolecular forces such as van der Waals forces, it is necessary to use a method that takes quantum mechanics into account. J-OCTA is used here. It is possible to evaluate the adhesion of materials and various interfacial properties. However, it should be noted that the scale of target is below the nanometer. The results shown here are for the adsorption of butane and hexane on gold and methanol on alumina. The capture diagram shows the stable structure during adsorption, and the top right graph shows that the results compare reasonably well with reference values. The blue color is the J-OCTA result, and the orange color is the reference value. Following the previous slide, this slide also uses J-OCTA to calculate the adsorption behavior of organic molecules on inorganic crystals. The lower left figure shows butane adsorption on a copper surface. The upper right graph shows the adsorption energies of butane, pentane, and hexane on the copper surface. The horizontal axis is the distance from the surface and the vertical axis is the energy. The dots are the DFT results, and the solid line is a graph drawn using force field parameters that were determined to reproduce the results. The force field parameters are those used in molecular dynamics. This means that it allows us to perform similar molecular dynamics on a copper surface on a larger scale. An animation of a molecular dynamics being performed is shown in the lower right-hand corner. This allows for calculations on the 10 nanometer scale, and is an example of a multiscale calculation. This could be useful to evaluate material properties related with dynamics. This slide is about the thermal expansion of the ceramic material. The temperature variation in the crystal cell volumes of potassium and KZP were studied using J-OCTA. Materials with a low thermal expansion coefficient are attracting attention in the miniaturization of devices. KZP is known as one of such materials. The volume of crystal structure at a certain temperature was calculated. It shows that the thermal expansion of potassium increases with temperature. The linear expansion coefficients of potassium and KZP are reproduced by J-OCTA. In addition, anisotropic thermal expansion of KZP was evaluated. This tendency is same with experimental data. This slide shows the curing reaction of epoxy resins. Using molecular dynamics, the motion of the molecule can be calculated on a scale of about 10 nanometers. VSOP is used as the calculation engine. In the left figure, the red color indicates the main agent, and the yellow color indicates the curing agent. After the calculation, the color of the molecule is almost entirely gray, as shown in the figure on the right. The same color represents one molecular species, which means that most of the molecules react and are connected to each other. The left figure shows the structure before the reaction, and the right figure shows the structure after the reaction. Using J-OCTA's reaction modeler, you can easily configure the atoms to react, the force field parameters, and charge redistribution after the reaction. The bottom right graph shows the time progression of the reaction rate. Since molecular dynamics computes nanosecond phenomena, we are looking at much faster behavior than real phenomena. But the final structure constructed is of interest here. In the reaction process in molecular dynamics, it is also possible to use the Based Monte Carlo method to determine whether or not the relevant atoms should react with each other. In doing so, we refer to the activation energy. We can use J-OCTA to calculate the reaction and evaluate the activation energy. The left graph shows the curve of distance and energy between the molecules. And the activation energy is shown in the graph. This result can be obtained by performing the calculations, as shown in the animation on the right. By applying uniaxial elongation to the structure obtained by reaction calculations, the stress-strain characteristics can be obtained. Again, it should be noted that a higher speed deformation was applied here than in the experiment. But the obtained Young's modulus is comparable to that of the experiment, because the epoxy resin is in a glassy state at room temperature. It is possible to confirm by molecular simulation how these mechanical properties are affected. When the molecular structure of the epoxy resin's main agent and curing agent are changed. This slide also deals with thermosetting resins. By performing a full atomistic molecular dynamics, a cross-linked structure can be constructed. The figure on the right shows the obtained structure, which is less than 10 nanometers in size. The temperature is gradually lowered, for the structure obtained from the reaction calculations. These graphs show the specific volume at each temperature. The red, blue, and green graphs show the results for the cross-linking ratio at 70%, 80% and 90%, respectively. The slope of the graph represents the thermal expansion coefficient, and the point at which the slope changes is the glass transition temperature. The point at which the slope changes is the glass transition temperature. On the other hand, it should be noted that the glass transition temperature is higher than in the experiment, because of the fast cooling process. Molecular simulations show how the degree of cross-linking, or the molecular structure, affect the physical properties of the material. The stress-strain characteristics are evaluated by applying uniaxial elongation to the structure. In the graph, red, blue and green represent the results for the cross-linking ratio, 70%, 80% and 90% respectively. The slope of the graph represents the Young's modulus. The increase of Young's modulus by the degree of cross-linking can be confirmed using molecular simulation. In this slide, the thermal conductivity is evaluated. Full atomistic molecular dynamics is used. Partial high temperature and low temperature region are set up. And the thermal conductivity is evaluated by calculating the temperature distribution in the steady state. Here we are dealing with the structure of the interface between the silica crystal and the epoxy resin. Silica particles are sometimes dispersed in epoxy resin to increase the thermal conductivity of materials, such as semiconductor encapsulation. We can use molecular simulations to evaluate how heat transfer changes at the interface by modifying the filler surface. In this slide, solubility is evaluated. We prepare the bulk structure of the polymer, obtained by full atomistic molecular dynamics calculations. We can evaluate how much the small molecule can dissolve in it, using a Monte Carlo method. The bottom left figure shows the distribution of the voids in the polymer. Using J-OCTA, these voids can be approximated by spheres, and the number of spheres of each size can be evaluated. We can also evaluate the free energy by inserting small molecules into the voids, and then calculate the solubility. The solubility and diffusion coefficient values can be used to evaluate the permeability. The diffusion coefficient will be introduced in the next slide. The diffusion of small molecules in polymers is evaluated in this slide. The bulk structure of the polymer, obtained using full atomistic molecular dynamics calculations, is prepared. We run the calculation for as long as possible with some small molecules in it. The animation is the motion of the oxygen molecules in polydimethylsiloxane. This material is used in soft contact lenses, where oxygen permeability is important to the naked eye. The trajectory of the oxygen molecules is shown in the figure on the right. The resulting trajectory can be used to evaluate the self-diffusion coefficient. The upper table shows the self-diffusion coefficients of oxygen and carbon dioxide, both of which are in good agreement with the experimental results. Full atomistic molecular dynamics is used to calculate the motion of lithium ions in electrolyte solution. The three molecular structures contained in the solution are shown on the right. It is possible to evaluate how the mobility of the lithium ion changes as you vary these structures and ratios. The ionic conductivity can be calculated based on the self-diffusion coefficient of the lithium ion. Molecular simulations can be applied to the design of electrolyte solutions for lithium-ion batteries. Porous materials, such as zeolites and metal organic frames, are attracting attention for their catalytic functions and gas adsorption properties. In recent years, the reduction of greenhouse gas emissions is necessary, and they are expected to be used for capturing CO2 from the gas mixture. Zeolite can have a structure in which Si atoms are replaced by Al, and various cations are included to satisfy charge neutrality. Here, we investigated adsorption isotherms for a Na zeolite, which is Na ion containing FAU type zeolite. Graph shows the calculation results of the adsorption isotherms. The amount of adsorption increased with increasing gas pressure. We also examined the behavior of the gas at different temperatures and confirmed that the amount adsorbed tends to decrease with increasing temperature. In recent years, 5G communication technology is becoming popular, and the development of materials suitable for high-frequency communication is progressing. In this case study, we evaluated the dielectric properties that are important for reducing dielectric loss. Dielectric dispersion, in the high-frequency range, can be calculated using full atomistic molecular dynamics. Complex permittivity was evaluated from the phase shift when an external electric field is applied to the system. We also calculated the real and imaginary part of the complex permittivity and evaluated the dielectric loss tangent. The results are shown in water, which is easy to verify, but can also be applied to resin materials. We'll start this slide with a case study of the coarse-grained model. This case study and the next slide relate to rubber materials. Think of the yellow area as rubber molecules, and the blue area as silica and other fillers. We are evaluating the stress-strain characteristics of the material when large deformation is applied. In the past, finite element methods were used for this kind of calculation. However, as you can see in the snapshot image, the size of the polymer chain and the filler are about the same. And it is difficult to describe the behavior of the polymer around the filler in terms of constitutive equations. So the coarse-grained molecular dynamics method is being used more and more recently. In full atomistic molecular dynamics, phenomena of 100 nanoseconds or less are targeted. On the other hand, coarse-grained molecular dynamics can deal with the relaxation behavior of rubber-state polymers, which requires calculations of microseconds or longer. This is a case study of rubber materials, using coarse-grained molecular dynamics. In the capture on the right, the green area is the rubber molecules and the red area is the silica filler. One represents the dispersion structure and the other represents the aggregate structure. The stress-strain characteristics of the material, when it is subjected to large deformation, in uniaxial extension, and then compressed back. The graph on the left shows the first cycle. You can see that the curves do not match up during the tensile and compression processes. This is called hysteresis loss. You can also see the difference between the blue line, which shows the aggregation structure, and the red line, which shows the dispersion structure. You can see a small graph at the top left, which is the result of the experiment. You can see that the simulation results are close to the experimental results. What is interesting is the second cycle, where we can see from the graph, there is no hysteresis in the second cycle. This is the same for the aggregate and dispersion structures, and the experimental results show the same trend. Due to the large number of fillers, the system size is several hundred nanometers. For this reason, a supercomputer was used to perform the calculations. In addition, a slow deformation rate has been applied, which is slow enough to describe the rubbery state of the polymer. This shows the mechanistic analysis of hysteresis presented on the previous page. Look at the image at the bottom left. A rubber molecule is connected between two black silica particles. You can see how the polymer is also stretched when the deformation is applied. And when it returns to its original shape after compression, it looks different from the original polymer. This may be one of the causes of hysteresis. This shows that by controlling the interaction between the polymer and the filler, the hysteresis or viscoelastic properties of the rubber material can be controlled. Coarse-grained molecular dynamics calculations were performed to understand the phenomena occurring during the electrode fabrication process, in order to improve the performance of fuel cells and lithium-ion batteries. The system consists of three components: filler, polymer, and solvent. The evaporation process is represented by the solvent escaping from the upper side of the region. VSOP was used to calculate the evaporation process of the slurry. The resulting porous structure was used to evaluate the diffusion and conductivity by muffin based on the finite difference method. VSOP was used to simulate the evaporation process, to obtain the porous structure, after solvent evaporation. Many particles are treated. An evaporation process requires long time calculation. So the supercomputer was used. From the results, the structures of particles, polymers, and pores were extracted, and their diffusion and conductivity were analyzed. These results simulate the diffusion and conduction of electrons, ions, and gases in fuel cells and lithium-ion batteries, respectively. The results indicate that it is necessary to control the adsorption performance of the polymer and optimize the porous structure to improve the battery performance. These results indicate that the molecular simulation can be applied to the design of mesostructures. This slide is about interface of polymer blend. Relationship between strength and structure of interface is important. These pictures shows breaking phenomena of thick interface, thin interface, and with compatibilizer, respectively. In some cases, thickness of the interface becomes over 10 nanometers. This scale cannot be treated by using full atomistic molecular dynamics. So we used coarse-grained molecular dynamics. About the interface with compatibilizer, breaking is suppressed compared with the case of thin interface. You will be able to evaluate and optimize the interface structure, based on stress-strain relationships. In this simulation, results of mean field calculation was used, for the initial structure of the coarse-grained molecular dynamics. This is because equilibrium structure is not obtained by molecular dynamics only. This is an example of phase separation calculation, for polyelectrolytes. Dissipative particle dynamics, a type of coarse-grained molecular dynamics, is used here. The red particles represent hydrophobic Teflon, the green particles represent hydrophilic sulfonic acid groups, and the blue particles represent water molecules. Phase separation calculations allow us to see how water forms a channel structure. In the electrolyte membrane of a fuel cell, protons move through these channels. Changing the molecular structure will change the channel structure, which has a significant impact on the efficiency of the fuel cell's power generation. Similar phase separation calculations have recently been carried out inside the catalyst layer, in the vicinity of the platinum catalyst. This slide shows examples of phase separation structures and mechanical properties of thermoplastic elastomers. The phase separation structures formed by triblock copolymers, such as styrene isoprene and styrene, have been calculated using sushi. The obtained phase separation structure can be used as the initial structure for coarse-grained molecular dynamics. This is a typical example of a multiscale calculation. The red particles represent styrene, and the yellow particles represent isoprene. In other words, the red region is glass, and the yellow region is the rubber state. Coarse-grained molecular dynamics is useful for evaluating the rubbery state. Detailed calculations can be made of how the styrene region breaks down during large deformations, the deformation of the polymer shape, etc. As you can see, it can be used in material design, evaluation about the effect of molecular shape on the properties of the material. This slide also demonstrates the connection of the simulation model at each scale. Here we see phase-separated structures. The blue domain is made of polypropylene and transparent domain is made of elastomer. The phase separation structure on the upper right was calculated by sushi, and the other two structures were constructed artificially. Each structure has the same volume fraction of polypropylene. We performed finite element analysis to evaluate the average Young's modulus. The graph is about the average Young's modulus of each structure. We can see big difference among structures. Circle is dispersed structure, diamond is bicontinuous structure, triangle is structure obtained by simulation. Important point is that each system contains same volume fraction of components. The difference of average modulus is due to phase-separated structure only. We can optimize the phase-separated structure to obtain appropriate properties. This is advanced simulation related with previous page. Phase-separated structure was obtained by sushi. And we used LS-DYNA. Nonlinear, elastic, and plastic phenomena were evaluated. We can see the concentration of plastic strain at the narrow region between rubber components. This is an example of a multiscale simulation of carbon fiber reinforced plastic. The cross-sectional structure of a UD material is considered here. The structure was created using DIGIMAT. The red area is the resin and the gray area is the cross-section of the fiber. Two types of structures were created, a dispersed structure and an aggregated structure. A cohesive element is used at the interface between the fibers and the resin. This allows us to handle the debonding behavior at the interface. The graphs represent the interface properties. Two types of interfacial properties are considered here. The blue line is the normal surface. The green line is called a modified surface. About the modified surface, the elastic region and the yield point are the same as for the normal surface, but it has the characteristics of being difficult to break. Finally, the deformation is applied in the direction shown in the lower right figure. LS-DYNA is used in this calculation. We need to make sure that the material properties of the cohesive element that we set up on the previous page are reasonable. Therefore, we performed a qualitative evaluation using coarse-grained molecular dynamics. The gray plates in the figure are the surfaces of the carbon fibers. The green area is the polymer and the red particles are the chemical bonds between the polymer and the fiber surface. This represents the modified surface. The polymer was set up as a glassy state and peel-off calculations were performed. The graph shows the stress characteristics. There is no difference between the elastic region and the yield point in the two cases, and there is a difference in the fracture region. This is the same tendency as that of the cohesive element in the previous page, so this demonstrates the validity of the parameters we set. Finally, we performed the calculation of the fracture using LS-DYNA. See the figure at the bottom right. This is a case where the fibers form a dispersed structure, and a modified surface is set. You can see, this case is holding up to the end. The aggregation of the fibers causes stress concentration. Also, if the interface is weak, it will quickly break down. After confirming the adhesion properties of the interface with molecular simulations, multiscale simulations for the design of fiber-reinforced plastics have been performed. This slide shows dynamics of entangled polymer chains at the melt state. In this calculation, we use the coarse-grained unit based on entanglement molecular weight. This model is called tube model, and we can calculate the long-time relaxation of polymer chains. The graph shows the comparison between the simulation data and experimental data about G' and G'. Target materials is polyisoprene with a molecular weight of 50,000. Simulation data is in good agreement with experimental data. Important point is time scale of this graph. We can evaluate the viscoelastic property with the time scale of over 1 second. Recently, it has become possible to simulate entangled polymers using dissipative particle dynamics. In general DPD calculations, the entanglement effect does not occur because the molecular chains slip through each other. Therefore, a virtual chemical bond called slip spring is introduced to obtain the entanglement effect. Here, we evaluated the G' and G' of polystyrene from the relaxation modulus. When compared to experimental results, good agreement was obtained for each molecular weight. From left to right, the graph shows the master curves for the molecular weights of 60,000, 112,000, and 271,000. This is case study of the viscoelastic simulation based on the tube model. Some entanglement points of the tube model were changed to cross-linking points, and 3 cases were compared. Red points are cross-link, and there are not cross-link around end of chain in the case 2. Tangent delta, ratio of G' and G', was evaluated. This value is related with rolling resistance. Low value is preferable. This results shows case 2 is not good because the tangent delta is high. This means, cross-linking around the end of chain is important to reduce the rolling resistance of tire. This case study is about the thermal conduction properties of carbon fiber reinforced plastics. There is a technique for mixing nanofillers, in order to increase the thermal conductivity of the resin part. Here we consider a nanocomposite, by blending graphene sheets into peak resin. First, we have calculated the dispersion structure of the graphene sheets, in the peak resin, using DPD. The obtained structure is then imported into DIGIMAT FE. The average thermal conductivity is evaluated by the finite element method. These are nanoscale phenomena. The next step is to calculate the micrometer scale. This is because carbon fibers have a diameter of 10 micrometers. In the carbon fiber UD material, we set the thermal conductivity of the nanocomposite, obtained earlier, to the properties in the resin region. The average thermal conductivity at this scale is evaluated using the equivalent inclusion method in DIGIMAT MF. Finally, thermal conductivity calculations for the aircraft parts are performed. The finite element method is used here. Here are the results of the calculations. The figure on the left shows the dispersion structure of the graphene sheet in peak resin, calculated using DPD. The upper image shows a normal graphene sheet and the lower one is modified with oxygen. The yellow particles represent the oxygen. The introduction of oxygen causes the graphene sheet to disperse. We now use this structure to perform a finite element analysis of heat transfer. The results are not shown here. Next, we calculate the average thermal conductivity of the CFRP using the equivalent inclusion method. In the upper right figure, we evaluate the properties in the z direction. The obtained results are shown in the upper right graph. The dispersion of the graphene at the nanometer scale affects the average properties of CFRP at the micrometer scale. Finally, the obtained properties were used to calculate the thermal conductivity of the aircraft parts. The bottom right figure shows the distribution of the heat flux. The green area represents the high heat flux. You can see that the green area is larger on the aggregated result. Again, we can see how the nanometer scale dispersion affects the macroscopic heat transfer. Thank you so much for your attention. If you have interest or any questions, please visit our website and share your comments with us.